Good morning. This is the first in a series of A-level math topics that I will be covering. So, primes. Well, you don't get graded in A-level maths for your spelling, I tell you what. P-R-I-M-E-S. So, what are prime numbers? Prime numbers, so let's call them P, are numbers that are bigger than 1 and are only divisible by the number 1, so P, 1 divides P, and itself, so P divides P. There is no number, let's say there's no number M, that's bigger than 1 and less than P, so that M divides P. So let's look at some examples of primes. So we have, well, 1 is not prime because it's bigger. Primes have to be bigger than 1. Well, this is just this rule came from the fact that using 1 as a prime isn't particularly useful. We call 1 a unit. It is not prime. Another unit is minus 1. So a unit would be anything whose magnitude. So a unit is 1. Okay, the magnitude of a unit is 1. This is the modulus function. You might not have covered it yet, but modulus. It just for what you need to know for A-level maths, the modulus just makes a negative number positive and keeps a positive number as it is. So not prime. So it is prime. So this is no. 2. Well, there's no numbers between 1 and 2, right? So 2 is clearly prime because there's nothing to even check. And yes, 1 does divide 2, and obviously 2 also divides 2. So yes, it is prime. What about 3? Well, we can check between 1 and 3. The only number between 1 and 3 is 2. And 2 does not divide 3, so yes, 3 is a prime. And you can check that 1 divides 3 and 3 divides 3. What about 4? Well, what are the numbers between 1 and 4? There's 2 and there's 3. So 3 does not divide 4, but 2 does divide 4, which means 4 is not a prime. So some of the first few prime numbers is 2, 3, 5, 7, not 9, because 3 divides 9. Next one along would be 11, then 13, then 17, then 19, then 23. Now you don't need to memorize these. You can always work them out in the exam. In fact, you'll probably be given a number like, for example, 97. And this is not prime. Actually, is it? No, it might be prime. You'll be given a number like this and you'll be asked, is it prime? So you could so far, what I've told you, the way you might go about checking it is you would check if 2 divides 97, and it doesn't. 3 divides 97. I hope you know that you can check this by checking if 9 plus 7, which is 16, is divisible by 3. This is just a trick to check divisibility by 3. You can do this again. 1 plus 6 is 7, and 7 is not divisible by 3, so we can say that 97 isn't divisible by 3. Or you could always go ahead and try and divide it, and you can just see that if you try and divide 97 by 6, you get a remainder of 1. 4, well, because 2 didn't divide, I should put cross across it, because 2 doesn't divide 97, 4 clearly doesn't divide 97 either. In fact, that means we don't need to check any multiples of 2 or any multiples of 3 because it clearly won't divide 97. So the next number we might need to check is, let's see, we need to check 5, okay, because 5 is not a multiple of 2 or 3. And clearly 5 doesn't divide 97 because multiples of 5 end in a 0 or a 5. What about 6? Well, 6 is a multiple of 2 and a multiple of 3, so we don't need to check 6. What about 7? Does 7 divide 97? Well, there's no tricks for checking if 7 divides 97, so we should just divide through and check. So we've got 97. So if you remember how to do division, I mean you might not, you do, there's 1 goes into 9. Well, 7 goes into 9 once, so we put a 1 on the top. And then 1 times 7 is 7, and we take it away and get 2, and we get 27. And we can do, what is it, 21, which is 3 times 7. And if we take it away, we get 6. Now, obviously 7 doesn't divide 6. So we see that 7 does not divide 97. Okay, and in fact we can stop right here. Okay, and you might not see why we can stop right here right away. It's actually not obvious, but you can, and this is because factors. So 97 is prime. This is all we need to do. So 97, we can stop right here and say 97 is prime, and in your exam you would be expected to say that. Okay, and this is because, and this is a fact, factors, oh sorry, this is supposed to be factors, it's not a fact, so factors come in pairs, okay, pairs where 1 is bigger, okay, factors of a number n come in pairs where 1 is bigger than or equal to square root of n, and the other is less than or equal to square root of n. So let's see why. Okay, so let's suppose we have a number 10. Actually, no, we need to remember all the loads of factors. In fact, it doesn't matter what number it is, but I'm going to pick one with loads of factors. So 12. In fact, I also need it to be like a square number. That would help. 36, right? So if we have a factor of 36, which is 3, then we know we can find another factor, which we multiply by 36. We can divide 36 by 3 to get 12. So 3 and 12 are a pair of numbers that make 36 when you multiply them. And in fact, any factor of 36 will make a pair like this. So 4, for example, would make 4 and 9, which make 36. So we're just finding 2 and 6 would also make a pair of numbers, although the two numbers in the pair would be the same. So if you notice, one of these numbers, and in fact we can actually write them the other way around too, that's totally fine. One of these numbers, for example 9, will be greater than or equal to the square root of 36, which is 6. And the other number, 4, will be less than or equal to the square root of 36, right? And in general, if we have a number n, we can write two numbers. So let's say m, or in fact d for a number that divides n, and n over d, two numbers that multiply together. I mean, you can clearly see that if you multiply these two, the d's will cancel and you get n. So, and these two are whole numbers, okay, integers. And one of them will be less than or equal to the square root of n, okay. And why does one of them have to be less than or equal to the square root of n? Well, if you suppose that d is bigger than or equal to the square root of n, then that means that dn over d, right, is greater than or equal to square root of n over square root of n. Actually, what am I doing? I need to just rub that up. Okay, so question. Why does one of them have to be, if we say d is less than n, why does this have to be greater than square root of n? Well, square root of n times square root of n is equal to n, right? Right, and if we say that we have d being less than square root of n, right, then that means that d times square root of n will be less than n, right? That means that square root of n over d will be greater than square root of n. So that's why one of them is less than square root of n and the other one's bigger. So that would be the proof. Okay, and that's about it. So so as a summary, primes are numbers that only have two divisors, which are 1 and itself. So you can check if a number is prime by checking if it's divisible by all the primes less than or equal to its square root, right? And why? Because factors come in pairs. And that's about it. In the next video, I will be showing you that there are actually infinitely many primes. So I hope you enjoyed the video, and that's about it.